Hello class and welcome to today's lesson. Today we are going to be solving equations involving exponential or logarithmic functions. So if you're in Algebra 2, this is section 6.6 in your textbook. For pre-calculus, this is section 3.4. So we're going to start off with some kind of warm-up examples, and then they're going to get more involved as we go through today's lesson. So to begin, if we want to solve this equation here, this involves an exponential function because I have a base with an x and an exponent. And if you're so lucky as to get a problem like this, you can just go ahead and write down the answer. We know 2 to what power gives you 32, and that answer is 5. So these don't happen too often, but if you see one that you can solve because you just know the answer when you look at it, that's called solving by inspection. So if you can just look at it and tell what the answer is, that's solving by inspection. Okay, number 2 is next. Number 2 is more complicated. The number 2 involves exponential functions again, because we have a base with an x up there in the exponent. We have a base with an x up there in the exponent. And there's a strategy that we can employ here. And that strategy we can employ is to rewrite both sides using the same base and then equate the exponents. And that's going to work here because I have 3 as my base, and 9 can be written with a base of 3. It can be written as 3 squared. So I'm going to just copy the left-hand side. I'm going to change 9 into 3 squared. So I replace 9 with 3 squared. And then using a little property of exponents here, if you have a power to a power, you're going to multiply those. And what we have is 3 to this power equals 3 to this power. So what we're allowed to do because of the property we discussed the other day is we can equate the exponents. So I can set this exponent equal to that exponent and then just solve this equation. So the 4 is going to have to get added to the other side. The 2x is going to have to get subtracted to the left-hand side. And we're going to get x equals 4 as our final answer. And for our next of our kind of warm-up problems, these are the quick ones for today. We have natural log of x minus 1 equals natural log of 7. And what we can do here, again, is use one of those properties from the other day. So if we have 2 logs with the same base, so this is natural log, they both have base e, and these are equal to each other, then we can equate the expressions that are inside the logs. So I can set x minus 1 equal to 7, and then just move the 1 over to get x equals 8 as my final answer, and we're good to go. I did put a little star next to this one because tomorrow that's going to get a little more complicated. When we utilize the property where we have 2 logs that are equal and we set the stuff inside equal, we're actually going to have to be careful of the potential for what are called extraneous solutions. But that'll be in tomorrow's lesson. That shouldn't happen to you at all today. Okay, continuing on our way. For the next problems, I'm going to ask you to solve. And we're going to give an exact answer and a decimal approximation to 4 places when possible. I say when possible because if the answer comes out nice, then you wouldn't give a decimal approximation. So just referring back to number 2 that we just did, like there would be no reason to give it a decimal approximation for this because 4 is a nice answer. There's no decimal part anyway. But a lot of times when you solve these, you're going to get a decimal that you need to round. So that's when we'll be doing decimal approximations. So here's our first example. Number 4. I have 3 to the 4x minus 7 equals 57. So the first thing you want to do is get that exponential function alone. So move that 7 to the other side by adding it. And we'll get 3 to the x equals 64. Now, your next thought might be, okay, I have 3 to a power. Let's rewrite 64 as 3 to a power. So that's a good thinking to try to do it like we did the number 2 from before. But unfortunately, we can't rewrite this as a power of 3 because 3 to the second is 9 and 3 to the third is 27 and 3 to the fourth is 81. I have no idea 3 to what power gives me 64. It would be some crazy decimal. So the strategy from before is not going to work for us here. So we need a new strategy. So here's the strategy. Once you've isolated the exponential function, so this is an exponential function. Once you get that all by itself, See, I can't move anything else away from it. I can't move 4 to the other side by dividing because 4 is trapped up in the exponent. And I can't move 3 to the other side because 3 is the base. So I've gotten the exponential as alone as it can be. Then what we're going to use is the definition of the log to rearrange. So the definition of a log is where we take the base exponent and other guy and rearrange to the other form with the base, the exponent, and the other guy. So the definition of a log said this exponential form is equivalent to this log form. So if we identify the base, the exponent, and the other guy, we can rearrange. So what's going to go by itself is the exponent. And then I'm going to have, for the base of the log, I'm going to use the same base I had before. And then the other guy is what goes inside the log. So if you find it would help you to label these as base, exponent, and other guy, because we haven't done that in a few days. Base, exponent, other guy, feel free. But if you don't need to, you can just go ahead and rearrange into the logarithmic form. And the reason this is helpful is remember what the goal is when we're solving. We're trying to get x alone. We know how to do that. To get x by itself here, we just have to divide by 4. So what we're going to have is log base 3 of 64 divided by 4. That right there is our exact answer. Please circle it, box it, label it as the exact answer. Because what we're going to do next is get a decimal approximation. So, and by the way, for anyone looking at 64 and 4, you cannot reduce those. I know 2 goes into 64 and 2 goes into 4. Actually, 4 goes into both of those. But you can't reduce them because the 64 is trapped inside the log. If I were to put parentheses around it, would that make it a little more clear that you can't reduce the 64 and 4 because it's not really 64, it's log base 3 of 64. But what we can do is use a calculator to get a decimal approximation. So if you have a graphing calculator that has the log base feature, which includes those of you using the online calculator from the PARC NJSLA website, you can hit math and scroll down to where it has log base. And you can put log base 3 of 64. And then once you get out of those parentheses, divide by 4. And you can get a decimal approximation for x. And you can round to the 4 decimal places. So 0.9464 will be your answer. For those of you who do not have a calculator with a log base feature, you have one extra step to take, and that's to use the change of base formula. So just to show you, because you don't have the log base feature, what you need to do is you need to rewrite log base 3 of 64 using the change of base formula. So you'll do natural log of 64 over the natural log of 3. So that's rewriting this using the change of base formula. It's one extra step. It's totally not worth buying a new calculator. If it really bothers you, use the one that's online on the PARC website. And what you'll do is you'll do natural log of 64 and divide by the natural log of 3. Watch those parentheses. And then when you divide by 4, you get the same answer that we had before. So same answer, whichever type of calculator you have. So the decimal approximation here is going to be x is approximately 0.9464. And let's go ahead and label that as the decimal approximation. And I will be asking you to label which is which, decimal approximation and exact, because I have found in the past that sometimes students aren't sure which is which, or they're not sure where the exact answer is. So we're going to start practicing right now in today's lesson with labeling which one's the exact and which one's the decimal approximation. For the decimal approximation, you will see that I use the approximately symbol. If you were to put an equals there, I won't take off. But just so you know, by the time you get to calculus, they actually, if you take AP Calculus someday, they do actually take off if you if you use equals when it should be approximately. I will not deduct points for that in Algebra 2 or pre-calc, but it's a good opportunity for you to practice your notation. And by the way, if anyone wanted to write down or circle this one as the exact answer, that would be fine as well. That's also an exact answer. Your exact answer is when you have x by itself and you can't simplify anything, and you can't figure out any more without taking out a calculator. So x by itself, you can't simplify it unless you pick up a calculator. And your decimal approximation is after you use that calculator when you round. That's what makes it an approximation. Okay, next example. Here's our next example. And this time the exponential function involves the base of e. And we're going to follow the same steps. So the strategy was to isolate the exponential function. We can move that 3 to the other side by subtracting it. And the exponential function is not yet isolated. So don't change to log form yet, because this negative out front can be moved to the other side. If you don't realize that that negative out front can be moved to the other side to create this equivalent equation, so this equation is equivalent to this one. If you were to think of it or rewrite it as -1 times e to the 2x plus 1, that may help. So if you think of this as -1 times e to the 2x plus 1, then you should see that you can divide both sides by -1, and you'll end up with that exponential equals a +2. This exponential is now isolated. You can't move anything else away because you can't move the 1 by subtracting it because it's trapped up there in the exponent. You can't move the 2 by dividing because it's trapped in the exponent. And you can't move e to the other side because that's the base of the exponential. So this exponential has been isolated. Now we're going to use the definition of a log to rearrange the 3 pieces. So here's my base, my exponent, and my other guy. My exponent will go by itself in the logarithmic form. The base for the exponential becomes the base for my log, and the other guy goes inside. Since this is log base e, I'm going to go ahead and rewrite that as ln. In our work, we can write log base e, but by the time we get to our answer, we should use the proper notation for natural log. And then we need to get x by itself. So we're going to subtract the 1 to the other side. You cannot combine the 2 and the 1. It's probably going to be tempting to make that natural log of 1, but you can't combine those. Let me rearrange those 2 terms for you. Instead of natural log of 2 minus 1, if I were to put the -1 first and then the positive natural log of 2 second, I think when you look at this, you would never try to combine the -1 and the 2. So same deal. You can't combine the 2 and the 1 here. Or if you want, throw that 2 in parentheses, and that might make it more clear that you cannot do 2 minus 1. Okay, and then to get x by itself, we're going to divide this entire quantity by 2. And this is a good exact answer. We have x by itself. I can't do anything else inside here without picking up a calculator. If you'd prefer this as, so those of you who, when I rearranged the -1 in the natural log, if that was, gave you a sigh of relief because it made more sense or looked better, then it would be okay to have this as your exact answer instead. Feel free to rearrange those. And now we need the decimal approximation. So whichever calculator you have, okay, we're going to do, let me show you 2 ways to do this. So because I'm going to do this one in the calculator. Because the numerator has 2 terms, we would really need to put parentheses around the entire numerator. So it would be parentheses, natural log 2. You want to close the parentheses because only the 2 is inside the log. Then subtract 1, then close parentheses because of the numerator. So that entire thing is the numerator, and then divide by 2. Now, that's a lot of parentheses to keep track of. So if that was like a little bit too much, another option for you is to just put the numerator in and hit enter. And since that denominator is just 1 term, you can just take that quantity, just hit divide, and then the calculator will take the previous answer, that's what the eqns is, and divide it by 2. So either way, if you want to put the whole thing in your calculator at once, you will need parentheses around the numerator because this has 2 terms. And what we'll get for our decimal approximation is -0.1534. If you'd prefer to write that as -0.1534, that's the same for our purposes. Let's go ahead and label that as the decimal approximation. I'll abbreviate because that's such a long thing to write out. And we have our exact and our decimal approximation for our answers. Okay. I have 2 more examples in today's lesson. So here's our next one. The next one is number 6. And we're going to continue to solve and give an exact answer and a decimal approximation. So taking a look at number 6, this is different than some of the other ones we've seen so far because there's no exponential function. So this is an equation that has a logarithmic function instead. So the first thing we want to do is get the logarithmic function by itself. We want to isolate it. So let's slide that 1 to the other side by adding it. And then the next step I want to take is to divide both sides by 2. Now, just to take a moment and note, you might be looking at this and thinking of the properties for expanding and condensing, because you can actually take this 2 and swing it inside and make it an exponent. You can do that, but you don't want to. You want to avoid the properties of condensing and expanding unless you must use them. In tomorrow's lesson, you'll see that when we use properties to condense or expand, we run the risk of making the equation more complicated because we can actually end up with extraneous solutions. Those are solutions that don't work, so we have to check our answers, which is more work for us. We also can end up potentially losing solutions if we use properties to condense or expand. So do not use those properties unless you must. So even though you're thinking, I could move that in and swing it up and make it an exponent, you want to avoid that because it'll be less work for you. If you don't use those properties, you're not going to have to go in and check your answers and make sure that you don't have extraneous solutions. And we're going to do more on that tomorrow. So what you want to do instead is divide both sides by 2. And let me actually show that step because sometimes the step I just wrote is not always obvious to people. So if I divide both sides by 2, see this is 2 factors. I have 2 and I have that log. So that's my first factor and second factor. So the 2's are just going to reduce, and that's why I'm only going to have log of 4x plus 7 on the left-hand side. And then this side reduces to 2.3. All right, so we've isolated the log. The base for the log, by the way, is 10 because it's common log. If no base is written in, we assume it's a 10. And here's the strategy you want to use. Once you've isolated that log function, we're going to use the definition of a log to rearrange and solve for x. I don't know if you remember, but when I introduced the definition of a log, I said this would be the answer to most every problem in the chapter. This is what we use when we evaluate, and this is what we use very, very often when we solve equations. So whenever you're stuck and not sure what to do, if you can get a log by itself, switch it over to exponential form. If you can get an exponential by itself, try switching it to log form. Very often, that's going to be the key to finding your solution. Okay, so we isolated the log function, and now we're going to use the definition of a log to rearrange and then solve for x. So taking a look at what we have, 10 is my base, 2.3 is my exponent because that's what's by itself in log form, and 4x plus 7 is my other guy. So it's going to be 10 to the 2.3 equals 4x plus 7. And then to get x by itself, we're going to subtract 7 and then divide by 4. When we subtract 7, I cannot really simplify because I have 10 to the 2.3 minus 7. And similarly, when I divide that entire side by 4, I can't simplify. So I can divide this side by 4 and divide this side by 4, but I'm not going to be able to simplify this answer anymore without picking up a calculator. So x is alone. I can't do anything else unless I have a calculator. I can't do anything else really without a calculator. So that's my exact answer, and we're ready for the decimal approximation. Why don't you try to get that in your calculator and see what you get for the decimal approximation. And I'm getting 48.1316. If you did not get 48.1316, what may have happened is if you did not put parentheses around the numerator, then the calculator did PEMDAS, but it didn't do what you wanted. You wanted the calculator to do that numerator first. So you have to tell the calculator that using parentheses. If you don't put any parentheses, you're going to get an incorrect answer. So again, two options here. You can either do the whole numerator in parentheses. That's because it's two terms. The denominator doesn't need parentheses in this case because it's one term. Or the other option for you, if you're kind of overwhelmed by all those parentheses, is just put the numerator in, hit enter, and then hit divide. The calculator will take the previous answer, and you can just divide that by 4. Either way works. So what you should get is 48.1316, and that's your decimal approximation. Okay. And one more problem to go in today's lesson. Here's our last one for today. It's number 7. So this equation involves a log function, not an exponential function. So here's our log function. And I switched the variable on you. I threw a t in just because it's not always going to be x. So I want to remind us of that. So in order to solve this, the strategy we're going to use is to get the log function by itself. So what we can move away is the 7. And we can move that 7 by dividing both sides by 7. I'm going to leave that as 12/7 because it would be some crazy decimal, and we'll just keep it as 12/7. Why not? You can make it 1 5/7 if you want, but I prefer the improper fraction over the mixed number personally. Just think it's a little more compact. Okay, so is the log isolated, or can I move anything else away at this point? The log is isolated. You can't move the 3 by dividing by 3. That's not going to move the 3 because the 3 is trapped inside the log. You can't move the 4 to the other side because the 4 is the base for the log. So the log is isolated. Now that the log is isolated, we want to identify the base, exponent, and other guy so that we can use the definition to rearrange. The base is 4, the exponent is 12/7, and the other guy is 3t. To finish solving for t, we'll divide both sides by 3. And this is good for an exact answer. You can't really do anything else without touching a calculator. So if you have one of the newer calculators, when you go to put this in your calculator, the calculator raises the exponent for you, and then you can use the right arrow to get out and just divide by 3. If you have an older graphing calculator, just be a little bit careful here, because when you do 4 to the 12/7, you are going to have parentheses around your exponent. So just be aware of that, because in the newer calculators, the calculator clearly shows that 12/7 is the exponent. And then when I divide that by 3, that'll work. Same answer. If you don't use the parentheses when you do 4 to the 12/7, what you're actually telling the calculator, you're telling the calculator to do 4 to the 12th and then divide by 7. So if you don't put parentheses with the older graphing calculators, if you don't put parentheses around the exponent, you're saying to the calculator, do 4 to the 12th and divide that result by 7. What you want the calculator to do is 4 to the 12/7. So that's why you need the parentheses around that exponent. Okay. So whichever calculator you have, you should end up with your final answer as 3.5891. That's your decimal approximation for t. And just to reiterate, just to repeat, anyone that has the older graphing calculator, these little differences, I really don't think it's worth buying a new calculator. You just have to be a little more careful with parentheses in some very certain scenarios. And if it really bothers you a lot, just access the one that's on the Park website for those few situations where you might feel a little bit annoyed with the older calculator. And that's it for today's lesson. Make sure you do the practice problems that I have posted, because tomorrow's lesson we're going to step it up a little bit. The equations are going to get a little more complicated, and we're going to have some new strategies as well as possible extraneous solutions. So do make sure you complete the practice today.